Now imagine that we switch the battery poles, meaning this side, this time, we connect the positive side of the battery to the p-type and its negative side to the n-type. So the positive side would push the holes in here, obviously. So the holes which are the majority carriers in the p-type would be pushed away. Since the electric field and the movement of the holes would be in the same direction, it means the electric field that this battery is adding is in this direction. And obviously we could say that the negative side of the battery is pushing the electrons away. Therefore, electrons would move in this direction. Again, the electric field is in the opposite of the movement of electrons, so electric field has to be in this way. So we say the electric field that this battery is creating would obviously be in this direction. And well, right now, this E field would oppose that motion. So if the E field resulted from the battery is strong enough to overcome this field, then poles would be pushed in this direction, and obviously they would go through the loop and be attracted to the negative side, and electrons would move in the opposite direction through the loop and to the positive side. Since we say current is defined as the direction of the movement of holes or the opposite direction of electrons, so both of them would contribute to the current, and you would have a current in the loop. So we say in this type, the p-n junction is acting in the forward bias. And we could just, you see, this is just another modeling that as we talked before about the abstraction as well. So we could make another abstraction in a higher level and abstract this as showing it as using a symbol like this, indicating that current could only be, because this as the p-type, this side as the p side, and this side as the n side. So we say current, let me change my color actually, we say current could only go from the p-type to the n-type. So we put actually this as a dam that we can't have the current on the opposite side. One could also argue and say this that we call a diode is like some kind of switch, because if we don't apply a voltage big enough to overcome the E field between them that has been created because of the diffusion, then the switch would be off. When we increase that electric field or the voltage applied to the p-type, that p should be more positive than the n-type by a certain amount, that it could be like 0.7 volt as an example, then we would have a current through the diode. Well, in that case, you could just, I guess, model the diode as maybe a short circuit, or maybe a resistor, or maybe a just voltage and a resistor, because I guess, well, yeah, I don't want to get deeper into the electronics, but what I wanted you to notice was that how many abstractions we used until we got to this diode as some form of switch. You see, we started from the nature and the atoms and electrons and protons and the valence shell, that atoms would like to feel their valence shell to be more stable. And this is, as a rule of thumb, we said there is the octet rule, that by filling their valence shell, meaning that they would have, most of them would want to have 8 electrons in their valence shell. Then we said silicon has 4 electrons in their valence shell, therefore it would make it a candidate to be a semiconductor, because when we put them next to one another, they would form 4 bonds, covalent bonds, and defined what it means with 4 adjacent silicon atoms. And we said as the temperature raises, some of the electrons in those bonds would obviously get some thermal energy, and therefore would break out of the bond and would become free, that we could direct it in some way by applying a voltage. And we explained that therefore they would leave a hole behind. And we defined how a hole is defined, that it just comes as an abstraction, that the movement of some other electrons into that hole is somehow, I guess, summarized or abstracted as a whole. I'm just using the word abstraction too much, but I think it's really important that you understand where we were and where we are now. So then we said, since current is defined as the charges times speed, or speed of the charges, therefore to increase the current, we need to increase the number of charges. So we did that using a method called doping. By doping, we had two options. One, to add phosphorus, since it had 5 electrons in its valence shell, therefore it would have covalent bonds with 4 adjacent silicon atoms, leaving 1 free electron without adding any hole. And we call that as an n-type. We also added boron, who had 3 electrons in their valence shell, therefore the opposite happened. We had the same number of, we had more poles, the same number of holes as we are injecting the boron atoms. And we explain how they are calculated. Therefore, we had the n-type and the p-type, and when we put them next to one another, since the concentration of electrons on one side was more than the other, and also holes the other way around, therefore, because of the diffusion, we would have the movements of electrons from the n-type to the p-type, therefore making n-type a bit more positive and p-type a bit more negative. So we made another abstraction and showed it as if we have a depletion region between p and n. And then we connected to the reverse bias. We explained what reverse bias is, that if the p-type is connected to the negative side of the battery, then what would happen? Because the majority carriers in the p-type are holes, so holes would be attracted to the negative side of the battery, and electrons, as the majority carriers in the n-type, would be attracted to the positive side of the battery. Therefore, we wouldn't have any current in between. We, of course, explained about the movement of the electrons from the p-type to the n-type and holes from the n-type to the p-type, and we called it the reverse current, I guess, and we showed it by I of S. But since we said the minority carriers are so small, their number, therefore we would have an ignorable current. The IS would be so small that a lot of times we just ignore it. And then we explained that, well, the more reverse it is, the more we could model it as if the depletion region is increasing more. And then we connected that PN junction to the forward bias, meaning the positive side of the battery now is connected to the p-type, and therefore it would push the holes in the other side, and obviously the negative side would push the electrons to the other side. So in a way, we said an electric field is created which opposes the first electric field, which was created because of the diffusion current. And we said that we need to apply a voltage that would overcome that E field. And we said typical values for that voltage would be like 0.7 volts. So we explained, we made another level of abstraction, and we showed it by this symbol, and we call it the diode. We said this diode, if the P side that we show it as here is connected to a more positive voltage than the N type, then you would have current in one direction based on everything that we have explained so far. We also said that both electrons and holes contribute to current, even though holes are another form of electrons, but we made a great example actually with the example of the soil. So, and also, I guess more importantly, we also said that this diode could also be treated as a switch, that it could direct, the switch could be on or off, but in the on part, it could direct the current only in one direction. So that's it for this lecture. I really think this was the most important lecture so far because it had all of the topics covered in one.